Hi everybody, welcome back. Hopefully you had a good uh weekend. Stay warm and cozy. So today we're going to talk about side channels. There's a little bit of lecture remaining on the sensor security as well that I'm going to finish it on Wednesday. Well, we wanted to do the side channel first and then finish that because I want to add a little bit to that lecture. Uh, Today we have Justin. Justin is my senior PhD student, fourth year PhD student, who works on side channels. So that's why I asked him to come and give us a guest lecture so that you see his perspective on this topic as someone who researched in this topic. He also gave this talk in other universities, so we thought that this might be a good idea for him to give a talk to our own students. He's going to give you kind of a background on side channels, which will like a classical lecture, and then at some point he's going to also share his own research, probably in the second part of the lecture. Before getting to that, a few okay, so scroll down. A few logistics, and then I'm gonna hand it over to Justin. Presentation is gonna start on Wednesday. This is kind of the most recent schedule. So people in week one, these are the guys who needs to present. The way it works is that the first line is the first paper, second line, third paper, fourth paper, fifth paper, right? It's on the website as well. You don't need to take a picture. Uh, there are small changes. So make sure that you see the most recent one. Important thing that you need to make sure is that your name is there. If your name is not there, let me know ASAP. Also, if you see your name twice, let me know ASAP. One last small thing is that this last group, I think is your group, right? I think you guys wanted to do W2, but W2 is already full, so I forced. We needed to move it to four. So that's the only group that is not doing what they wanted to do. Everybody else is doing what they wanted to do. Any questions about the presentations? I think if I counted correctly, there was a total of 65 people. There's still 7 people who didn't sign up, and the sign up deadline has passed. So you guys, those who didn't sign up, not gonna present and not gonna receive points for presentation. I don't know whether they want to drop the course. If there is something you want to, if you like, forget or something happened, email me. Maybe we can figure out and squeeze you in. Otherwise, just know that. But you have to do it like within the next few days. Second thing I want to talk about is the final project. I created this Excel sheet and shared with you on CampusWire. What I want you to do is going through this Excel sheet and put down your names of the groups and then a short description of the project you want to work on, and a little bit more comments description of what you want to do. I also put some kind of potential projects ideas. Essentially, the idea of the final project is for you to do a little bit more research and kind of understand a little bit deeper about the topics that we discussed. Few different things that you can do. My suggestion is probably the first thing you want to focus on would be sensor security. You can try to work on the attack side or on the defense side. On the defense side, things that you can possibly think about is various different detection mechanisms, such as machine learning, which is kind of what most people do these days. Think about new ways of encoding data and so on. So these could be potential research idea that you can do. You can also try to recreate some of these interesting attacks. We discussed a bunch of them last week. You're going to see a lot of them this week as well. And there's also plenty in the literature. You don't need to necessarily just implement those that we discussed. A few kind of comments I put here. One thing that could be very helpful for you is using generative AI for like generating data sets or validating your data sets and all. So feel free to use that. This is very helpful. And if like, large language models and generative AI in general for sensor data is actually very, very useful tool. You can also use open source data sets. A lot of these papers that we discuss and exist in the literature comes with data sets. For example, there's very good data sets on deepfakes. There's good data sets on time domain, audio signals, and so on and so forth. So for example, if you want to do a defense, one good thing is that taking these data sets, run a bunch of these different, techniques that you think about, try to see if you can, for example, detect an attack or so on and so forth. You can also think about if you want to do some physical measurements and physical attacks. There are equipment available both in our lab and the IoT lab, which is open to everyone. We can also, in some cases, buy some equipment subject to being useful for our lab. I can help and buy it. You can also, if it's not very expensive, you can consider buying it yourself and keep it for yourself. But when you're deciding on your projects, think about the complexity of the setup. You're probably not going to be able to, like if you need an access to very expensive and very elaborate equipment, probably not a good idea for that project because you're only going to have like 4 or 5 weeks to work on the project. So pick something that is reasonable within that time frame. Okay, so that's one option. The second option is side channels or fault attacks. Again, attacks and defenses. All the things I said for the sensor security applies here as well. Think about using generative AI or open data sets. Side channels, a very useful thing for side channels is this device called Chip Whisperer, which you can actually measure power side channels, electromagnetic side channels for it. Today, as you will learn about side channels, then you will be able to use that. Another thing for side channels is that in order to make your life a little bit easier, digital side channels also counts, although we're not going to talk much about digital side channels as you will see in this lecture, but like things like Spectre, Meltdown, Kite side channels, if you want to do projects on them, that's also fine. And lastly, another thing that you can do, and it's also fair game, is machine learning security and privacy in the context of IoT systems. So things like adversarial machine learning, attacks and defenses, large language models these days are getting a lot of traction and a lot of interest in terms of security. So things like jailbreaking, prompt injection, hallucinations, things like that. On Wednesday, I'm going to talk a little bit about adversarial ML. But this course is not particularly focused on machine learning as a topic. Later on, at the end of the course, I'm going to also talk a little bit about LLM security as kind of one advanced topic, but we're going to go very deep into it. But if you want to explore, and this is again something I realize that many people want to do, given that machine learning was very popular, in the context of IoT, many of these things are very relevant. So, for example, if you have a device like a voice controller that use some form of machine learning or large language models to make decisions, if you can fool it in order to make some adversarial decisions, that counts as a potential project. Another thing that I also extensively work on is privacy preserving machine learning. Again, like protecting data privacy, sensor privacy, and then defining projects in that domain also counts as an interesting project that you can work on. And the good thing about these is that for those of you who want to do something in machine learning, that's an option. I'm also open to other ideas. We're going to spend a good amount of time in this class on memory safety, binary analysis, and so on. So if you want to work on a new fuzzing, binary analysis, things like that, that could be also a possibility. We're going to also talk a little bit about suspicion and T's later on the course. So that might be a little bit harder for you if you don't have the background. But again, if you already have a background and have ideas, you can work on those things as well. So that's kind of like the basic ideas for the projects that you can work on it. Last thing before I give it to pass it to Justin, to do for your project. The first thing you need to do is putting your name in the form, okay? And you need to do this by next Friday. In order to do that, you of course need to decide on your groups and your topics that you want to work on. So talk to your friends, talk to your teammates on the presentation, because you already have a few teammates hopefully for your presentation. That would be probably a good starting point for you guys. Talk to them and see which of these projects are interesting, and then start thinking about what you want to do realistically. once you do that, then put your name down in the Excel sheet. If you don't have any ideas or don't know anyone, another thing that you can do is that the reason I shared that Google sheet with you is that you can actually go and see who are the other groups and if they're potentially open to getting new teammates. Put your name down there and then contact them and say you want to work with them. You can also advertise your project ideas on CampusWire, as some people already did. Once you did that, as I said, you need to finalize all the details by Friday of next week. And then after that, after Friday, I'm gonna send kind of an appointment scheduler for you to schedule a very short appointments, like for 5 or 10 minutes, so that one member of the group can just quickly describe what they're gonna do and what they want to do, and then give them some feedbacks and help them to kind of kick it started as soon as possible. I'm going to share the details of that next week, but this would be basically just to finalize and formalize your projects, final projects. Okay? Questions? Great. So we're gonna talk about side channels, just since I'm gonna leave. Actually, let me give my bag. But I'm gonna see you guys on Wednesday, and feel free to ask all the questions from Justin. Ask hard questions.
All of them.
But he is very knowledgeable and he's done a lot of great jobs on side channels, so he knows more than me on this topic. Yeah, 2 questions. Yeah, one.
Okay, so the final products, like signups, are due this Friday or next Friday?
Project signups next Friday.
Oh, okay.
Mm-hmm. Mhm.
The first step, like you say to separated by bytes. Do we have to do this manually? Can we just use like the inbuilt class on function?
It's better to do it manually, so it's kind of like the idea is that you write everything yourself rather than using built-in functions. Any other questions? I'll be in my office after the class as well if anyone has any questions. Okay.
Great. Awesome. Thanks, Daughter, for having me speak here. Yeah, everyone, I'm excited to be here. My name's Justin. I'm a PhD student under Nader in my 4th year. As Nader said, I've been doing a lot of research regarding side channels. So I'm really excited to be able to share a little bit of a window into my research world. I'll give a little bit of a backstory on side channels and some exciting works in that area, and then also transition towards this new area of research, an area of using side channels for useful purposes, which I've been working on in my PhD. So I'll get to that in all due time. But yeah, as we've been discussing in this class, there's a lot of systems, devices, IoT that you may have heard of, where you have this heterogeneity, lots of devices with different compute powers and etc. We're all interfacing with these in our daily lives. The question, though, is this tech is very pervasive and heterogeneous. The question, though, is that a bad thing? Is there any downsides to this new kind of age of devices that we're in? And that's where we get to this idea of the leakage of information. I guess to raise your hand, how many people have heard of Spectre or Meltdown before? Okay, so a couple people. But yeah, in the news, several years ago, there's this attack on Intel and AMD chips called Spectre and Meltdown. They're actually 2 separate attacks, and it broke the internet in that time. There was a lot of policies and adjustments to architecture that needed to be made after this, and it kind of broke open, it opened the door for more side channel research and the need for side channel research. And here's, as I was going through just the news of side channels, I found another one where turns out there is a security exploit where, say, an adversary who, say, is near, like, say, like a house, maybe they have like a video camera that's like inside, by just externally measuring electromagnetic waves from that camera, they could actually reconstruct the image. So you can see how that can be very privacy invasive, because previously thought information is now can be revealed to adversaries. I'm actually going to be talking about this attack later because I found it to be interesting, so I wanted to look into it. So more formally, what are side channels? Essentially what it is you have some system, it's doing some compute, and there's going to be some leakage. It could be, say, via like a power trace, it could be electromagnetic emanations, it could be temperature. But essentially, the adversary can measure this leakage and then extract something from it. So typically, these behaviors are not really thought of as if a system is deemed secure, like they're not thinking of like, say, like electromagnetic waves emanating from the device, potentially leaking information. So you can see how this can break a lot of security and privacy assumptions in systems. And it can be a danger if it's not covered for. So as I said, there are various types of side channels. I'm going to classify them into two separate types. There's physical and there's digital. And as Nader said, we're not going to talk too much about digital side channels this course. He's actually teaching another course in the spring called, I don't know exactly what it's called, but it's Security and Architectures, where he'll discuss more of the digital side channels. But as he said, feel free to explore this in your projects. But today I'm going to be focusing on the physical side channels, the ones on the left. And these are the ones that I've been primarily researching in my PhD as well. Yeah, any questions up till now? So the basic overview of this talk is I'm going to kind of slowly get into some of the assumptions and tools that the adversary has. Then I'm going to go into some foundational attacks that have existed in the literature. Then I'm going to go into a more exciting, interesting attack, which is the video camera one. And then I'm going to go into other usages of side channels. So what exactly are the adversary's goals? The goal is to basically extract something that could be sensitive, revealing, that they shouldn't have access to. The prime example in the literature is cryptographic keys. So you often, if you're reading a paper, you'll see, okay, like some chip is running some encryption algorithm, which has some secret, and via measuring some, some characteristic of that chip's operation, they're able to, say, extract the key when they shouldn't. You can also extract things such as programmatic information, like what exactly is running, so more like a profiler. So there's been works that said, like, via some power trace, we're able to see that this is this encryption algorithm, it's this program, etc. Another example is covert communication. So some people have used side channels to actually transmit information in a way that they shouldn't be able to. So specifically meant for the exfiltration of data. If you look into, say, digital side channels a little bit more, especially Spectre and Meltdown, they use a side channel to basically transmit information from some process out into the world. So covert, it's called a covert channel. You might see side channel and covert channel in the literature. Covert channel is essentially a side channel. It's just that the covert channel is being used to actually like intentionally communicate something out to the world. Versus like a side channel, it's just unintentionally emitting something, and we're just analyzing that. So this for these attacks, the kind of like crux of it has to be measurable in some way. Depends on the attack exactly, like the setup. But a lot of these can be measured externally. So for instance, for electromagnetic emanations, you can use some form of antenna, some form of probe to then analyze, to measure over the device. This requires you need to be relatively nearby, generally. There's some side channels that have actually been shown that you can actually extend the range based on some properties. So there's this paper called Screaming Channels, if you want to look into this, where they were able to basically see a side channel at essentially Bluetooth range based on the way that the side channel was operating. But the idea is you need to be kind of nearby, and at least in terms of physical side channels. It requires some form of measurement equipment. So as I said, for like electromagnetic waves, you need some form of like probe, some form of antenna, receiver to measure it. And many of these attacks require a fine-tuned, sophisticated signal processing and or machine learning algorithm to conduct. So you get a bunch of signal, that can be like your data set. And then you develop some form of algorithm to then classify, figure out which key it is, etc. So that's where a lot of like the research in side channels goes in, is like you have a bunch of this data. Supposedly there's no correlation between the data and the chip, But then like, our role or whoever's the researcher's role is try to find that correlation. How exactly do we find that correlation? And that's via this toolbox. I've listed a few tools that like I've used, I've seen used, but this is not an exhaustive list. But I see a wide or a focus on, say, time domain and frequency domain tools. So by time domain, you have some form of signal. Maybe it's like a voltage versus time trace, a power versus time trace. And a lot of people look at, say, correlation, differences, etc., to then extract information. Frequency domain is one that I've actually used a lot. So something such as like a Fourier transform to extract frequencies from a complex signal is really useful because then you can look at things such as peaks, signal strengths, and this can be really revealing about the underlying execution. There's a few more, there's some intermediate representations, but the basic idea is that you can use any like kind of statistical tool, machine learning you want to extract this. Like you might not even need to use, say, time domain, frequency domain, like specifically, you might just say, okay, let's just have some machine learning algorithm try to figure it out for us. So that also works too. But all of these require you to have a bunch of data, because data is gonna what help you learn the correlation. So how exactly would that measurement look? So I divided it to make it simple. I divided the setup into two phases. This is like a training phase. So for instance, you might have like, say, for instance, a copy of the victim device. I just put a Raspberry Pi here because why not? It could be any other device. But then here you have the attacker and the measurer. This is just a sample picture. So you might have some form of receiver. In this case, it's like a software defined radio, which is like a programmable receiver. And then you have a, say like some antenna. It could be antenna, it could be some other measure, but that's the one in this picture. We're gonna measure some aspect of the signal. And then on the right-hand side, we're gonna, train something. So it could be our algorithm, it could be our model, basically our master code book to basically say, this is what's happening in this device. And then we obtain more data as much as we can. Such that when we go to the testing phase, here we have the actual victim device now. And when we measure it, we can use that toolbook, those measurements that we've had in the past to then say, oh, I recognize this signal. This is key 1, key 2. Such that we can actually reveal the secret value, which is on the right and it's getting cut off, but that's okay. So that's kind of the general gist of this, where you have some form of, you need to measure, you need to analyze, and then in the testing phase, when you're like actually trying to attack, then you can use that past learning to then kind of infer what's happening in the real device to actually reveal. Okay, so that's about it for the kind of gist of general side channels. Does anyone have any questions up to this point? Okay, great. Yeah, and feel free to stop me at any time. You can just raise your hand. For now, I'll keep going. Okay, so I'm going to begin with like the very kind of most simplest form of attack, which is called differential analysis. Basically, what we're going to be doing is we're going to be collecting some time series traces, a bunch of them, and then we're going to kind of compare it to our test case and basically see if there's any relationship between the test case and then the collected traces that we've had. So how that works is we make some assumption about the unknown value. So if the value is, say, key 1, we're going to say, okay, let's assume that it's key 1. Classify samples based on this assumed value. And then the idea of differential analysis is then we're going to compare the difference between the two groups. There's two things that could happen. If our assumption of what we guessed the value is not correct, basically there's going to be no relationship between our kind of collected traces and then the actual test case, in which case there is no information to gather. So essentially these traces, the traces and the test case there should be no correlation, in which case there will be essentially no peak, nothing to measure. But on the other hand, if we assume that value was actually correct, the behavior is gonna match what we expected, which is gonna result in some relationship between the test case and what we assumed, which is gonna result in some correlation, which is gonna be a peak. So to kind of put a little bit more visual here, because I think showing it visually is a little bit more effective. So you have, say, like your chip, which is like your system that you're trying to attack. In this case, let's say we're looking at an encryption algorithm. We have some plain text, which is just our benign value, and then it's going to be encrypted, and we're going to have some ciphertext. And then everything in the red is going to be kind of like the attacker's analysis, where you're going to say like measure some aspect of this chip, and you're going to essentially analyze that with all the traces that you've seen in the test time. Basically, you just have a bank of a bunch of summer traces, and then you're going to be doing some comparison between the collection of traces and then the trace you collected. And the result you have over here is what you're going to be essentially going to be analyzing. So this is what I mean, where if your guess is correct, you're basically going to see that spike there, that peak is going to be essentially showing that there is a lot of correlation between our assumption and then the test case. If the guess was incorrect, you're going to see this flat line because there's basically no relationship between the test case and your assumption. So it's kind of almost like a brute force thing where you see what you're observing, you cycle through a bunch of different assumptions, and you basically see which one stands out. And that's why it's called differential, is because we're seeing essentially the differences between the different signals and such. So this is like the very kind of beginning. This one has some limitations because this is only one kind of view of like the execution, right? Like we're just looking at like a singular trace. As you guys are probably thinking, potentially with say like machine learning, lots of profiling. Basically, there's so much information that can be extracted from these devices. So that's where the next kind of classes of attacks kind of improves upon this model, is instead of just looking at, say, like one version of it, why don't we kind of build up some complex profile called like a template. So I'm going to introduce template attacks. Basically, taking this attack a step further, we're going to use a copy of the victim device in, say, like an offline phase, like away from the victim. And we're going to actually build like a complex profile template of the execution. And this template could be based off of many factors. It could be statistically based, it could be machine learning based, but we're going to build a very complex template based off of the execution, such that during like the actual test time, we actually don't need a lot of samples. In this case, like the benefit of the template attack is we're able to just measure it once and then use all of that like training and profiling that we've done beforehand, such that it like minimizes the time of the attack, because that increases the feasibility of the attack. So like if you're reading side channel papers, just always be just aware of the assumptions they make, because the assumptions that they list will they can kind of make or break the feasibility of the attack. Because if they assume really strong things like you must have physical access to the device, then it's going to be like a little bit hard. Like you say like they have to like actually like touch the power cables and such, like it's going to minimize the impact of the attack. But if like, oh, we're able to externally measure this without physical access, then it makes the attack a little bit more feasible. But just an aside. But yes, so the main thing to remember is that during test time, we don't need to measure a lot of signal, and that increases the success of this attack. And we can use the template of the device to then successfully attack. So I've already talked through these attack steps, but here they are again. You just want to train by running lots of inputs through to obtain lots of outputs, and then you're going to hopefully be able to get the secret key. So here's a visual. So 2 phases, training and test. You have your copy of the victim, and you're going to be just cycling through a bunch of different inputs, such that during your pre-processing phase, you're then going to, these signals can be noisy. One problem that I faced in my research is the data, or one problem that you could face in your projects is that these signals can be very noisy. There's a lot of other factors that can impact the cleanliness of the data. So you often need to pre-process averaging, slicing, etc., to actually get your data suitable for learning. And then you have some form of template generation. In this case, it could be modeling. It could be looking at statistical measures like covariances using machine learning. And then in the testing phase, then if it's RSA key 2 and you measure it, and you compare it to the template, you get key 2 out. All right. So enough of the background. So I'm going to get into 3 different case studies. The first case study, when I'm done, is a template attack on RSA. The next one I'm going to do is, instead of looking at, this was electromagnetic based. The second one, I'm going to be looking at a power side channel, just to give you guys a different view. And then the third one is extracting video via electromagnetic signals. So what I've done is a single decryption EM based attack. And it's actually on OpenSSL's actually most secure version of RSA at that time. And they're able to extract the key via those emanations. And I just want to kind of go through this to kind of motivate the template attack. And then did Nader go through RSA? I think he went through cryptography, right? But did he go through RSA a little bit?
Yeah.
It's essentially a public key. It's like an asymmetric encryption algorithm. But so basically RSA requires a lot of essentially like multiplications, square operations, and lots of works in the space for key attacks. They analyze the characteristics coming from those large integer square and multiply operations. One thing though is that these operations depend on the actual ciphertext, so it basically results in there being some noise in the data modeling, which can make the attack a little bit harder to realize. In this work, what they found is that in the implementation of the RSA in OpenSSL, they actually found a computation window between those large integer multiplications that is independent of the ciphertext, which is able to basically increase the clarity and strength of the noise that you're measuring. So as I said, like, you have higher SNR being signal to noise ratio, and they're able to improve upon, or they're able to get this attack to work even in the presence of prior defenses. So you can kind of see how in side channels there's kind of like a whack-a-mole thing that happens where some research labs, some PIs like, oh, we found this like attack on some said system, and then and everyone's like, oh, we got to defend against this thing. Oh, this is horrible. And then another attack, oh my gosh, like that assumption's like broken now. Like we finally, so this is kind of it's very similar to other works in security, but it's especially prominent in side channels. So it's an interesting area of research to pay attention to. I'm not going to get into this algorithm. You guys don't need to know this, but basically the only thing that I want you guys to remember is that there's this routine called essentially called Montgomery, which is their implementation of kind of like the encryption algorithm. There's a squaring of the result that happens, and then this is going to happen in this loop, and it's going to happen multiple times. Now there's this little section here, kind of in between the multiplications, where there's essentially looking up of some said bit. There's looking up of a bit, and that's going to be the I'm going to draw on here. So there's the secret. I guess the part of the key that's important is that there's these two kind of values, m being the modulus, and then d being the secret key, or the secret exponent, and these both make up the key. So this middle part is actually dependent on that value d. So if we can have this window here, run it through, and then find some correlation between the exponent d and the trace that we get, we might be able to reveal the secret key. So this is what the trace actually looks like. So this was in their slides actually. So this constant time Montgomery multiplication, squaring the result happens. There's a bunch of stuff that happens here. And what they found is that there's this very deterministic behavior that happens where right when you get to the end of your right when you get to the end of that multiplication thing, there's this very easy to find window right here in the middle that happens every time before, say, the next Montgomery multiplication happens. So this is actually measurable. And what they found is that that key window that I was kind of referring to is right here, right in this block. That's kind of like your crucial section where they are updating that window value. So what they did is we're gonna zoom into that a little bit more and see how they can extract some value. So this is a zoomed in view where you have the window value update. So in those dotted lines is where I was kind of zeroing in the prior figure. But basically here you have two traces, A and B, and then you have, I say, two values we tried, 0 and 1. All you need to know is that the red lines are relatively close to each other. The black lines are relatively close to each other. So basically runs for bit 0 and runs for bit 1 are similar. The key part is that there's difference between one runs for 0 and runs for 1. So here you can see there's a gap between these two wavelength signals, and same over here, there's some gap there. So if we can look at those and kind of extract those, you might be able to say extract bits 0 and 1, which then is going to be the foundation of our attack because we want to extract data. So they then conducted this attack, showed some, there's more to it. If you guys want to read more, you can look at the paper. But then they trained on a bunch of 15 RSA decryptions, and then they conducted the template attack in reality to see what you can get. Here's an example of a physical setup. So this is a setup that I'm very familiar with in my own research, where you have some device that's in the foreground, which is like your device under test. It could be like some device like that. And then there's going to be some like measurement that's happening. So I think this wire over here is going to be the measurer. And then you have over here, you have some, like oscilloscope spectrum analyzer to then measure. I realize this color is not the best contrast, so I'm going to change it to red and then make it a little thicker. I think that should be better. Yeah, it's a little better. But yeah, they tried it on 3 different devices, and what they found, I'll zoom in a little bit here. Basically, they wanted to test this attack. I guess on the y-axis is you have accuracy, on the x-axis you have the actual device. So number one is the device that they trained on. And then 2 through 8 are like new devices that you've never seen, but they are the exact same type as device 1. So for instance, if this is an Arduino, these are also Arduinos, but like it's not the same Arduino. It's like an exact copy of it. So you can see over here, I mean, the accuracy is pretty darn consistent. I mean, the one for self is quite high here. But if you're looking for 2, 3, 4, 5, 6, it's 99.5%. It's splitting hairs there. So it shows that basically this attack is generalizable, because like if your attack works on your training, it's no point if it doesn't work on your testing. But here they show that it's applicable to all these, and of course there's going to be some variance, but that's okay. Like if you're at 99.5, like you're chilling. So that's the end of the one and done attack. I guess if I were to summarize it in one sentence, template attack on RSA using electromagnetic emanations on the RSA OpenSSL routine. Is there any questions on this paper? Yeah, question.
So that like update window frame or time?
Yeah.
Is that when it is trying to copy that value D to somewhere, or is that trying to confuse something?
Yeah. So go back here. Yeah, so there's this window value here, and it's going to be updated based on actually the secret part. It's in part due to the secret key here. So this function bn is bit set, and it's dependent on D, which is our key. And that's that like small window of opportunity that we have where we have some operation that's dependent on the secret key, and it's not, say, like dependent on ciphertext or anything.
So it's just like trying to copy to buffer and
Yeah, essentially. So this window value is then going to be used in in later. Yeah. Yeah. Because I think in this one it's going like window by window. So you have to kind of update based on the window and then yeah. I also in the slides I have the paper like cited. So if you want to actually look at the actual paper, on the first slide of all of them, I actually have that there. And it's on the website too. Okay. All right. So now I want to do an attack on a power side channel. Just to give you guys another flavor of side channels and how it's not just electromagnetic emanations. There's also ones on power. So there's one paper that I've seen cited a lot. It's called FPGA-based remote power side channel attacks. This one's really interesting because in the cloud, I guess a lot of workloads when they're divided amongst their in the cloud, they have a lot of co-located processes. It could be like FPGA. You could have different logics on say some said FPGA. So we're kind of particularly looking at this kind of scenario where you might have like an attack logic, victim logic co-located. Can we actually measure something that's happening in the victim? So what they found is via a ring oscillator and some extra circuitry that I'll get into, an adversary can actually infer some information about a victim's execution, which they should not have access to because like these logics are supposedly isolated. And it could be either on the same FPGA or it could be on the same SoC. So if you're looking here, this would be like an example of like an FPGA in some data center. And you can see how there's attack logic and there's victim logic, and these are like separated. So there's no actual direct access between here, except for the problem is, as we'll find in this paper, is that there is some leakage that is actually occurring that can actually be measured, which then obviously breaks any security assumptions that we made. And in the other case is we have a combined FPGA and CPU SoC in the data center. So as the attacker, we shouldn't have access to the core 1. Core 0, which is also an attack process, should also not have access to core 1, which it doesn't. But here, via the attack logic, we're able to extract some signal here. So there's a lot of details, but if I were able to distill it into a simple idea, is that this power consumption can actually be correlated with the secret key value. And how is that? Is a ring oscillator circuit can basically function as a voltmeter. So by taking some simple circuit like that on the right, essentially the frequency that your data is going through that ring oscillator actually is a function of your power. So if you're able to measure that oscillation frequency, then you're able to basically extract the power consumption at that time. And if you're able to extract the power consumption at that time, you can correlate that to values, and then you have your attack. So they developed a couple circuits. You don't need to understand what's exactly happening here, but they basically use a ring oscillator counter to basically measure the frequency. The frequency being, oh yeah, question?
So is this just measuring like the clock frequency of the CPU?
So are you referring to oscillation frequency?
Yeah, is that oscillation frequency of that circuit just measuring the clock frequency of the CPU?
Oh no, so it's measuring the frequency of the data kind of passing through. Because basically it could be a function because like the temperature and things like that affect it. And but I guess in this case,
Isn't the frequency the data flows through just the clock frequency?
CPU? Well, it depends on the circuit. I think in the ring oscillator case, I don't think it is. If I might be wrong. But I just know that there's some correlation between the rate that
Or are they just saying like when the frequency scales up, it usually uses more power, like because of like dynamic voltage frequency scaling?
I think so. Yeah, something like that. I'm gonna look into this a little more after. But yeah, I also have the paper here if you're curious. Right there. But the basic idea is this ring oscillator is going to be oscillating, and there's going to be some. It correlates to power. And one thing that's important about side channels is that it's noisy. So instead of just looking at one of these ring oscillator counters, we want to look at multiple. So multiple being like in space. So like it's physically divided across the FPGA. Why don't we measure this thing multiple times, have multiple measurements, and then like aggregate the scores? You get better resolution by aggregating. So in fact, what they found is that they did a bunch of, so basically they put this thing called a power virus. It's basically correlating to more power usage. And they put all these power viruses on the FPGA. And what they found is that there's some linear relationship between that, the oscillation frequency that essentially that your ring counters are measuring and the amount of power you're using. The x-axis is basically saying more power goes to the right. So you can see that there's like this linear relationship, which gives us our ability to basically measure how much power we're using. So if we zoom in on an RSA power trace, so here being like the sample count we're measuring, and then power monitor output is just a measure of our power. So like higher number means more power. So basically you see how this trace is basically oscillating between high and low at pretty discrete steps. So we're able to basically correlate like those different values to 0 and 1, which is then able to help us extract our data. They also did had some results for the SOC. So basically what we're saying is that there's this big dip that occurs between like right here and right here. And that's going to basically correlate to execution of the CPU execution of string compare. So you basically have this like ability to see the power. So it's pretty crazy how like even as an attack logic, like even if you're not like you don't have access to the victim logic, like if you're on the same like FPGA, you're still able to get some information out, which is crazy because like this is on the cloud, right? So like you could be anywhere, like you could be some process or you could be some attacker and you upload your logic onto some FPGA and then it's like co-located with the other ones. They're supposedly isolated, but then you're able to measure something, which is pretty neat. Okay. All right, so I'm gonna go through one more, and then I think we can give you guys a 5-minute break, or I guess I'll ask you guys if you want a break or you'd rather just keep going. I'm gonna go through one more case study. I thought this was one of the more interesting ones I'd seen because it kind of has a lot of system level aspects of it. So it's called EMI. Characterizing electromagnetic side channel eavesdropping on embedded cameras. So on the right hand side here, say you have some like room, it could be like a hotel room, it could be an office. There's some camera that's like recording, it could be recording anything. In the attacker's case, they're hoping it's something sensitive. And basically the attacker right here is able to use some measurement to then basically get the signal out from this camera. There's some trace that's happening. And the attacker then is able to generate, in this case, an actual like reconstruction of what's the camera is actually recording, which is pretty crazy. So how do they do that? So here's like a broad diagram of a camera. So, or like a measure system. So you have like this camera, and then it's basically going to transmit some data over this this image data interface. And then like here is your kind of processor. It's going to do all that stuff, that processing. Basically what they found is that this image data transmission step is going to be leaking electromagnetic waves that correlate to essentially the rows, columns, and frames that you're sending as part of this video. So that's kind of like the key insight is that as we're transmitting or sending data from our camera sensor to the embedded system controller, we're going to be leaking some electromagnetic waves. So what I mean by rows, columns, and frames is that here on the over here you have your essentially your pictures, because videos consist of pictures. And over here for B, you have your sensor, and it's going to be transmitting data across that wire in some predetermined format. And if you measure the electromagnetic waves, like say like their amplitude across different timestamps, you're basically able to kind of section off like where certain things are happening. So over here in C, here is basically showing 2 frames. So you can see that there's like a gap between the 2 frames. So you see that the electromagnetic amplitude decreases between frames. So you can see that you can kind of segment off where the frames are. And then on over here, you have actually 10 consecutive rows. So between rows, there's like a gap. So you can actually segment in time when a row is occurring. So that in of itself is not enough, because like we don't like just knowing that a row is sending, that a frame is sending is not enough. So that's where we need some notion of like color. So like we can't really make a picture unless we have like color, whether it be grayscale, RGB, or whatever. So in this final column, they basically set out to show that there's some correlation between color and amplitude. So if you look on the first picture, you're going from a lighter color to a darker color. And what they saw is that the amplitude goes from higher to lower. So like, just remember like in RGB, like lower values are darker and then like higher values are like lighter. So you can see how like the value, it's like a little high and then it goes down. And then this also happens, lower down in the picture, same thing, higher and then lower. Now, and then in comparison, when the color does not change in your row, it stays very flat line across the trace. Stays very high in the case of that greenish color, and then it stays low in that darker color. So what they actually did was that they actually used the amplitude of the EM signal as but they end up doing grayscale. They use the amplitude of the EM signal to be essentially the value of your pixel. One thing that I found interesting in their pipeline was that looking at different like electromagnetic frequencies reveal different parts. So in this part, we were looking at like one frequency in the space, and we're able to get this kind of characteristic. But what in these like cases where you have more complex pictures with lots of like edges and detailing, they found that it's useful to actually do the same measurements across multiple frequencies at the same time. So in here, they did it at 204 megahertz and 255 megahertz, and then you essentially get 2 different pictures that are, say, more optimized for certain details. So if you have like different pictures that are optimized for different details, why can't you, combine them? So like you have these 2 pictures, why don't you just say combine them to make some like, master picture, your final picture, which is in fact what they actually do. But before they get there, they need to get the correct image. They just make a few assumptions on some of the model parameters. And this signal that they are getting, this EM signal to reconstruct the image, is going to be essentially, you're essentially demodulating it because you have some signal that's going from high to low. So you're basically looking at the amplitude of that signal to basically get your value. So here's a high level view of that pipeline. You have a camera image over on the left, and it's going to leak via that sensor interface. You're going to be leaking some electromagnetic signal, and you're going to be looking at different frequencies. Over here, you're looking at frequencies 1 through n, and you're going to get like different traces, and these are all going to correlate to different different pictures that all kind of focus on different things. Now, when you combine them together, you're going to get some higher, hopefully you get a picture that's higher quality than the ones that you started with, because otherwise, what's the point of that? But and the final step is here, image to image translation. It's a little bit of a complicated term, but the thing that I got from it is that given a picture that's a low resolution, you can use features of the picture to actually like improve the quality. So like if you can kind of see, swaths of same color, you see, while it might be like a round edge, you can kind of make out certain, objects. You can use that information to then extract a, sharper image, which is essentially your way to clarify your output. So here's an example of a setup. One thing that I think this was a very simple setup, where they basically had a camera pointing towards some picture, and then you had some like measurement setup. So here they use this USRP, which is like a software defined radio, and it's connected to some antenna. And just know that this can be extended to like what is called like non-line of sight scenarios. So I know it's not showed like this in this way, but the idea is basically if you have some directional antenna, or say like outside the room, you can measure like these emanations can leak through walls, as I've measured in my experiment. So you can be like outside a room, you measure the electromagnetic emanations outside the room, you then collect them, you do your measurements, and so on. Okay, so this is a lot, but basically what they had is some ground truth. So they wanted to identify how well they were able to match the caption of a picture, which is like the bottom row, and then also detection of faces. So in here, it's like a kitchen with a stove, refrigerator, sink, and a microwave as the ground truth. And here's like the state of the art. So I guess in a lot of research, they like to compare against the state of the art, to see what's the kind of like the baseline that we're trying to improve on. And you can see it's not performing well. It's not able to label correctly. And then here I have it on the Raspberry Pi 4B, but they also tested it on other devices as well. And you can see that the label is relatively close. This one's missing microwave. I guess they're both missing microwave. But you can see it's a lot better than the state of the art. And you can see in the face detection, they're actually able to detect both faces for both of those. Any questions on EMI? Yeah.
So was state of the art in this paper here, do you like other papers prior attempts at doing stuff like this?
Yeah, correct. So the fun thing about research is like you're building off of like prior papers, prior works. So there's a bunch of other state of the works they cited. I can't list them off the top of my head. But one common thing to do in your papers is like, okay, like other works did similar, but maybe less optimized things. Maybe they had made weaker assumptions. Maybe they had different scenarios, but like that's your kind of comparison point. Like, okay, like this is what has been done in the past, so we can compare it to that, and then hopefully we can improve upon that. But yeah, these are just like prior papers, prior works. Anything else? Okay. So I'm at the kind of inflection point where I kind of talk about defending against side channels, because I've been talking about a lot of leakage of information. So like, I think it's important to talk about how we can defend against these things, because like not all hope is lost. So in the physical domain, we can do a lot of things. So like in the electromagnetic space, right? Like you hear of, shielding. So for instance, thinking about like metal. So you can hear of like Faraday cages and etc. Like if you have some sensitive thing, you can like surround it in material that prevents these signals from being leaked. Air gapping is another thing. So like what that means is like, separating your device from like the network, from other people. Things such as like constant time programming can improve reduce the effect of the adversary's attacks, but just know it's not foolproof. There's always, especially as computing's getting better, there's always some like the tools that the adversary has access to is always increasing. So all these assumptions that you make always need to be revisited. think the basic idea is you want some form of randomness because what the adversary is doing is they're finding some correlation between execution and like the signal you're getting and the data that's being ran. So you just basically want to randomize it to an extent, which is frustrating because as a person in tech, you want your things to be fast, but then sometimes security sometimes comes at odds of that. So then one interesting area of research is like how we can have secure functionality that's like fast. Because like we want to have good performance and security. So that's what a lot of like people in like in architecture research are doing is like they want to have fast compute while also having security. There's a few things that they can defend against digital side channels, isolation, also randomness. So there's a few things that we can do. Just note that these side channel attacks kind of come, they go, and then they come back. I think Spectre has been around for, it's still around. I think there was an attack on iPhone Safari browsers that used a version of Spectre that literally just came out again. So it's very quite interesting to follow. Okay, before I get into the next part, I guess raise your hand if you would like a 5-minute break. And then raise your hand if you would not like a 5-minute break. Okay, I think there are some people that didn't vote, but that means we're gonna get a 5-minute break. So let's get back at like 5:10, and then we'll conclude the lecture of side channels for good. Oh, wait.
Oh, yeah, well, they close right. I don't know what
Wait, honestly, like, you literally told me that, I don't know, it's like watermelon. But like, there could just be like a gap here.
All right,
Might not
let's
be.
go ahead and get going. I guess you guys can talk more after class. Who had the question on the ring oscillator? Are they still here? Okay, well, if they come back, I'll make a point on the ring oscillator. But yes, the final part of this lecture is side channels for good. You might be wondering how. It's like side channels bad, good is good. So how does that work? Basically, this leakage of information can be a good thing. As you can see, like this information can be used to learn about the device. So we should be able to use that for more useful things. Also, was it you that had the question on the ring oscillator by chance?
Yeah.
So I was looking at that actually during the break. So the ring oscillator essentially consists of an odd collection of inverters, and these inverters, this circuit is going to be not clocked. So the rate that some data will go through the circuit is entirely determined by the delays that you get through the circuit, and it's related to essentially the properties of like the CMOS and capacitance that you get. And then that oscillation frequency is going to change depending on the amount of power consumption that's going to be that's drawn throughout the FPGA. Does that make some sense? Okay. Oh yeah, question.
Well, is that because like heat transfer between all the different circuit components, or because you're actually directing more power to the ring oscillator?
Could you repeat that?
Is because like the ring oscillator speed or frequency changes depending on power consumption. I'm asking, is that because you're actually feeding more power to operate the ring oscillator, or is it because the ring oscillator is indirectly affected by like components next to it?
Yes, it's the latter. Because so they basically, if you kind of draw out the FPGA, say you have your ring oscillator over here, and then basically there's this thing called a power virus, and they basically locate these all on the FPGA. These things are all going to be drawing a lot of power, and this frequency, the oscillation frequency of that ring oscillator is going to be indirectly affected by all these power viruses running at the same time, and it's going to result in essentially the frequency going down. I guess the idea is like as like temperature increases, like as basically things slow down because it's just like there's more resistance. That's kind of like the principle. Yeah. Great. Okay. Side channels for good now. So I'm gonna start with some like works in the literature, and then I'm gonna go over one of my works to explain a little bit of this. The first one is anomaly detection. So a lot of systems they might have like bugs, malware, whatever, and it would be useful if we could have some form of an analyzer to basically say like, oh wait, we actually have something going on here. We need to. This is deviating from the expected behavior, so we should do something about it. So that's where the class of like anomaly detection, malware detection comes in. In this paper that I'm citing, it's basically detecting a row hammer attack. You don't need to know what a row hammer attack is. If you want to learn more about it, it's in Otter's architecture course. Basically, it's a software caused hardware fault. Basically, in your memory, if you basically access repeatedly certain rows, they can accidentally affect surrounding rows, which is bad because then you're like the attacker is then able to attack or affect data, which is not good. So on this trace here, you're basically looking at the EM spectrum for different activities. So comparing playing a video versus hammering the DRAM flash, DRAM via CL flush. So you can see there's some commonalities, right? Like in the center is the clock. So the clock is going to be one of your strongest sources of signal because the clock is always going to be running. It's always going to be at some said frequency, so it's going to be very strong. Now, if you're playing a video, you're going to be doing some accesses to memory, some to like the network, so you're going to get some spectra. What they found is for DRAM, there's this very strong activity off in the sideband, and if you notice, there's actually like a relationship between these two because the difference in frequency between the left and the right is exactly the same. You can say they're mirror images of each other. So basically, like they're essentially related to each other. That's how the modulation works essentially. But besides the point, basically there is some behavior in the spectrum that can be analyzed that correlates to said instruction. You can measure it across a certain time length. You can observe that you're having some hammering happening, then you say, okay, we can fix our system to adjust for that. Another one that can be done is program tracing. So there's this paper called Savat, and this is actually fun fact, this is written in part by Notter's advisor from Georgia Tech, so if you're interested. So this one's a methodology for measuring the side channel signal available for an attacker. So this is like, we have some code. We want to see how much side channel availability is there potentially for an attacker. Like it's essentially a measure of how secure our execution will be from potential listeners, as I'll call them. So they're basically looking at the differences between different instructions. And the key idea that they use is they were looking at the frequencies in the frequency domain and not the time domain to increase robustness, because time domain can be very noisy sometimes. But then if you look at the frequency and the periodicity of certain events, it can increase your SNR a lot, and you can actually extract something useful. Detection of spy cameras. I actually like this one because I just talked about a video camera one, but that was not a spy camera. And also I like the paper name, the Eye of Sauron, for you Lord of the Rings fans. Long range hidden spy camera detection, especially in the kind of age of like Airbnbs and hotels. People are always concerned about spy cameras. This paper is a really nice paper if you're interested in like kind of a system level design of like from an end-to-end system where you're able to basically detect a spy camera and then be able to actually localize it in the room positionally via looking at electromagnetic radiations. And I like this paper. It did a lot of neat things, putting together a lot of different aspects of the literature. Basically what they did is that based on these cameras, they ingest information into their memory based on scene changes. And that information, that kind of ingesting of into memory is then gonna release these electromagnetic waves. So based on the amount of change that they are imparting onto the scene via their measurements, they can basically infer how close they are, because like the stronger the signal is, the closer you are to it. So like that's the idea of like the signal essentially dissipates as you get further away, because basically like channel will, all these disturbances will attenuate is what it's called. So then they're able to use that to positionally localize. All right, so now I want to get to communication. So this was actually my first paper that I wrote. So this one holds a special place to me because like it was my first paper. But it's like everything has its bad side and good side, turning processors to low overhead radios using side channels. And the way that I like to kind of frame this is a way to communicate wirelessly without an antenna. You're like, how do you do that? So I'm gonna kind of walk through this. And then after this, I'm gonna kind of conclude with like takeaways that I want you guys to remember from this talk. So how does communication generally work? You have a transmitter and a receiver, and this transmitter, you want to send some form of message that then is going to hopefully make its way to the receiver. So then you use some form of modulation, you send it over the antenna, the data transmits over all the way to the receiver, and then that receiver is able to decode the message using the opposite, like using the same properties of the modulation scheme to then get the message. So the questions I'm asking is like, how is it possible to actually communicate without a transmitter antenna? So what I proposed in this is, or me and my advisor proposed, you have a transmitter and you have some message. We have some way to actually transmit data, no antenna. It's able to transmit over here. We're able to get some message, and this provides lots of benefits. Like number one, we don't need an antenna radio. Number two, this radio can be very power hungry. So a lot of lightweight IoT devices are like maybe they're intermittent, they have limited compute and power constraints. So it's like these radios like are very power hungry. So it's nice to not be able to have that. And if we can use some form of hardware agnostic transmission capability to then transmit, that would be really nice to have. So basically, it's a completely software controlled communications paradigm where you have some function that runs a set of instructions, basically your code. And basically that combination of code is going to basically emanate some form of signal that is going to correlate to the data that you're trying to send. So there's a lot of things that there's a lot of challenges that are faced in going about this work. Like number one, like how do we actually communicate something like anything? And then number two, how do we actually encode more things? Because like 0 and 1, nice, but we want to send things, fast. But then also another challenge is how do we send it robustly? Because like you want to send it with high accuracy too, right? Like you're sending it over to the channel, so there's going to be noises and interferences. So we also need it to be robust to those changes as well. So that's the kind of the challenges that we needed to address in this paper that I'm going to go into. But first of all, like how is this even possible? Because before you get into the advancements, like you got to figure out like what is kind of known in the past. So I'm going to get into a little bit of kind of this hopefully maybe I should have done this at the start, but I wanted to save it for this part because it's like really important for this paper, where I'm going to get into how like emanations happen, because like I've been talking about these emanations a lot, like what are they? So hopefully this helps clarify that a little bit. So you have some processor that's going to be on like like your CPU. And there's going to be some, crystal that's going to be like your clock. It's going to be oscillating at some certain frequency, and it's going to result in some like voltage time, like square waves. And it's going to be oscillating up and down at your clock frequency. And basically what that's going to do is that this oscillation at your CPU is then going to cause changes in your circuitry. the way that I think it's easiest is that basically your circuitry is going to be consisting of basically a ton of capacitors and transistors all connected to each other. And based on the changes in your wave, you're going to be basically getting changes in your capacitors and transistors. So basically, if it's like high, your electrons are then going to then accelerate through these circuit components, and if it's zero, then they're going to decelerate. Why the acceleration deceleration matters is there's basically this old formula of Faraday's law where basically there's a change when the accelerating and decelerating of these electrons caused by this kind of oscillation changes the magnetic flux, which is going to be this factor here. So basically a change in your magnetic flux is then going to cause essentially your electromagnetic field. So that electromagnetic field is that electromagnetic emanation that I've been talking about this whole time, where basically what's happening in these circuit components is then causing some measurable electromagnetic field in the space. And it's in this case, when we're just running this clock, it's that clock frequency I was talking about earlier, where you have a strong spike in, this is the frequency domain, where you have a spike at the frequency of the clock. And it's going to be very strong because the scene is repeating over and over and over again. So that's great and all, except for the problem is, like, this is not enough to like transmit data. Like, this is nice, we have some clock, but like, where's the data going to go? Like, I don't know how to do that. So we need some way to actually encode the message. Basically, is there a way to take this clock, encode the message somehow using that clock? The idea is we can borrow from a technique used of how messages are traditionally encoded in radio frequency, which is modulation, to do the work for us. So I don't want to get into too much detail of amplitude modulation, but I guess amplitude modulation, if you guys are familiar with like, AM radio, that's essentially what amplitude modulation is. Basically what they're doing is they're encoding the data in terms of the amplitude of your output signal. So you can see this modulated wave. You have your kind of signal kind of inside kind of this shape, but then it's like oscillating, like the peaks are oscillating or like changing based on the data you're sending. So you have some data you want to send. All these modulation schemes are intended to work at higher frequencies. So you combine it with some carrier wave that's going to be at some upper frequency. So for like Wi-Fi, it's like 2.4 gigahertz, for instance, or like Bluetooth. This is essentially what's able to basically take it up to higher frequencies. And then when you amplitude modulate these, then you're going to basically encode that message wave into your modulated wave, such that a receiver looking and finding that modulated wave can then, the goal is to get this message wave out. So the question is like, is there a way to actually amplitude modulate the clock? Like, the clock is a very strong wave that's at some frequency. Can we actually amplitude modulate the clock? The answer is yes. So if you're looking at this code, you have some loop, and say you have some like heavy activity. By heavy activity, I mean like something like, I guess one example is like you can do memory accesses, you can do multiplications, basically anything compute heavily. Basically this heavy activity results in increased electromagnetic amplitude due to its high compute and power need nature. And if we pair that with a light activity, you can think of it as like an idle, like a simple add, etc. You're basically gonna get, here you can see, and then the first case we have like increases in amplitude. The second case we get decreases in amplitude. That could be some form of amplitude modulation, of some clock. So if we can carefully craft some code to change the amplitude of the clock specifically in some deterministic fashion, we might be able to actually communicate something. But to make it more realizable, we need to talk through exactly how that happens. So this hopefully should explain it. If you guys have questions, let me know. But basically you have cyclic code. Cyclic code is basically referring to the over here. Specifically looking at for loops. Reason why we're talking about cyclic code is because this shows up really well in our frequency analysis. You know, all that frequency analysis stuff I talked about before. If you run things at for loops being something that repeats over and over again, it's very useful in terms of this modulation. So what we do is we run some code multiple times across multiple iterations at some frequency. So this code is gonna finish at some period of 1 over delta F. And you know, using the properties of like the high activity and the low activity, you're gonna be basically getting this kind of pseudo square wave like behavior. That's gonna be basically changing the amplitude of your clock like very repeatedly. Now, what they found is that amplitude modulation kind of also appears in the frequency domain. So if you're repeating something over and over again, it basically, the amplitude modulation shows up in the FFT as a spike. So basically these two spikes are going to be exactly correlated to the frequency that this thing is kind of finishing at. So using some cyclic code with like heavy and light behavior, repeating over and over again, we're able to get some peak in the FFT that can be measurable at distance. That's going to be the key feature that we developed in this paper, is kind of creating spikes like this at some set frequency. The part that I need to get into though is that this is just one spike, like great, but like, can we send more spikes? Like, how do we send more like data faster? Like with one spike, you can only send so much. So that's where we can actually, instead of using one delta F, what if we use multiple delta Fs? So in this case, like you change cyclic code at delta F1, then you do delta F2. So like basically the spike is going to shift over to the right a little bit. Basically the higher the frequency, the higher, like the further the spike will go in the FFT. And then for so on and so forth. So the idea is that we're getting this slant, this kind of approximated slant like this. There's this protocol called LoRa. Is anyone familiar with LoRa? Like long range? Okay, there's a few people. But the benefit, so basically for those that don't know, LoRa is a long range, low power modulation scheme. Basically, it basically embeds the data as like energy in slants. So slants being something like that. And basically why they do that is because it increases the robustness of your transmission. And you're able to send it at long range for like not too much power. So it's very good for like lightweight IoT protocols. But like those still require like some antenna. The benefit of this work is that we're able to create some LoRa-like scheme that does not need the antenna. So by purely changing the code via some simple parameters, basically to change the rates that these things finish at, you're able to get some said slant. So by iterating through different delta Fs, we can emulate a chirp. I guess specifically what those delta Fs are is if I go up here, there's these like repetitions here that's happening. This is essentially going to change the period of your square wave. Like if you make this rep value higher, this for loop is going to take longer to finish, in which case it's going to like basically slow down that square wave, in which case your spike is going to go to the left a little bit. And if you want to move the spike to the right a little bit, you just decrease the repetition count to be less, such that this kind of for loop finishes faster. So that's how you kind of change the location of the spike, and you can do that to get different slants. And why a slant is good is because like you can basically encode different values. So I think the simplest way to do it is I'll show an example. It might not show up too well here, but I'll try to highlight certain parts. Clock is the center. It's very strong. And we have some bandwidth that we're getting. Here, I'll draw over this actually to make it a little bit more clear. So value 8. So it's basically dependent on when it starts. So for instance, the value 8 looks like this. So the x-axis is time and the y would be like, I'd say frequency. Yeah, frequency. So basically at time 0, it starts halfway up, and then halfway through it starts at 0. And then the value 0 would just basically be a slant like this. So you see at time 0, we start at 0 and it goes all the way up to like the uppermost value. So you can see how we can divide the frequency into different chunks and then basically encode different values depending on when it starts across, and then across that same time duration. So all the different values have the same time duration, like up till this point. But then what basically encodes the values like where the starting point is. So like in this case, like it starts, for 8, it starts like halfway through. Okay. So then we did this, what's fun about this was we did a lot of experiments across different parts of UCLA. So like for instance, inside, outside. We didn't do anything to shield the measurements. So we just wanted to have our communication being occurring, like not shielding any of the other external noises in the environment, etc. We tested 2 devices, Arduino Uno and a TI MSP430. I've observed this behavior in many others. These are just the 2 that we tested on at the time. And for a receiver, we used another software-defined radio, and we used TB antenna, and we just wanted some form of antenna to measure distance. Oh yeah, question.
How expensive was your software-defined radio?
Okay.
Is it like a very high-end one you need for this, or like a cheap one?
Okay, so it depends. So the USRPs, I guess the thing is, back in the day, they were like $1,000 or less. I think nowadays the USRPs cost more for some reason. It's been like harder to get them. This also works using cheaper software-defined radios. So for instance, there's one called a HackRF that's like I would say like $200, $300. There's also like RTL SDRs that are like $40 to $50. I think
Those ones work on.
I didn't have an RTL SDR on my hand. I probably should try that. That'd be fun. So I have an RTL SDR in my lab, but I have not tried it. But basically the better setup or the better receiver you have, the higher chance you'll be able to get it. But you don't need, say, like I think the most expensive version is like a spectrum analyzer. That's going to be like a couple thousand. So my via my past research and experience, something like USRP slightly less should work. I think there just could be some sacrifices. Like if you go cheaper, your for instance, your range might not be as high. So there could be like, some trade-offs. Yeah. So line of sight scenario. So this was just in our lab. We had a device in the foreground and then we had a receiver in the background. And we also wanted to do it out. I forgot what happened. I think one of the reviewers was suggesting that we did like outdoors experiments. So we did outdoor ones. And it was funny. It actually, speaking of the rain that happened this week, these experiments had to happen like right after it had rained, and there was like a steady drip from the roof. And I was outside, and I was like, after like 5 minutes of measuring, I went back and like there was like a small puddle like 3 inches from my device. I'm like, that was a close call. But my device was okay. So then we measured the SNR, signal to noise ratio, and you can see that we get reasonable signal strength across different distances for the different devices. The idea being that we want to be able to communicate something at long distances. So even 10 meters plus, we're able to, get something. And in addition to so by line of sight, that means I have a direct like angle to the device. But like, what if I have like a non-line of sight scenario? But with that, I mean like, what if there's like a wall around it and you might be know exactly where this was taken. So like, for instance, if this is around a corner, or like what if there's a wall? It's like, I mentioned like these things can be measured across walls. Like, can we measure this through a wall? So then we also measured the SNR. So we're able to get reasonable SNR through this. In the paper, we also looked at power consumption and bit rate and bit error rate. So you can look in the paper for those. I just wanted to kind of show this for this presentation. And so basically, we wanted to show that they're called chirps, these slants, but basically they can be measured at distance and through obstructions with resilient SNR. Any questions on that? Yeah.
What about like something like could you use like a trace on the board as like an antenna by like switching on and off something over that trace? With that,
A trace? What do you mean by like a trace? Like you mean like
like some sort of wire on the board that's
Ooh.
kind of long, like let's say, or maybe like even like let's say for example, you had an LED,
right?
And you could switch on and off this LED.
Yeah.
And that there's a wire to the LED, like the short wire, like
Yeah.
LED on the board, right? It
Yeah.
has to go on the wire as it turn on and off.
Yeah.
That work?
That might. I know there's been a lot of works on looking at like cables. So a lot of like display cables have been, or a lot of emanations based attacks have been like, oh, like the cable is like emitting something that's like the transmission of data from one part to another is actually leaking information. So I don't know about your exact case, but I know there's been other cases where some said wire has led to some leakage of of information to an extent. But what's interesting is like I don't know, maybe it does do something. I guess I'm not sure exactly what the I guess the one trade-off would be probably range, just because like I think the processor, like the clock itself, like in regards to your CPU, is probably stronger, but like it's going to be some function of that, like to change the LED. So maybe, yeah. You have a question?
Oh, I wanted to ask like why is the signal to noise ratio like better for the MSP 430 as compared to like the Arduino?
So yeah, so we were so for our setup we use like an an external clock. But the actual device itself, in our case, you're able to get higher SNR. It really just depends on the actual device. You kind of just have to go out and see. This is what we observed using our setup. But there's a lot of factors that kind of affect the SNR. The one thing that's good about LoRa though is that LoRa demodulation has been shown to work even below the noise floor being below 0. So there's a lot of LoRa is a very resilient protocol. So like even if like another device was like kind of lower, we would still be able to extract something. Yeah.
What's the data rate you got?
The data rate. I forgot the exact number. I think it was around. Actually, like here, let me pull it up just just to make sure. I'm pretty sure it was 900 bits per second. It's going to be a function of essentially how fast you can or it's basically a function of like how much information you're able to encode in your chirps. Here, like pull it up right here. I'm pulling up on my own screen here. So we have. Yeah, so this was bit error rate. Yeah, so we did it across lots of packets, get lots of bits. Yes, so we were able to get around 1 kilobit per second. So that's, so I guess one point I'd like to make is, let me share this again. Okay, so one point that I'd like to make is that so the use case we envision this for is especially like lightweight IoT devices that need to kind of send data, say like periodically. Obviously, if you want to send data really far at a really fast rate, you're just gonna have to go with like some antenna. But like that's a trade-off, right? But if you want to send some data, spawn it out periodically, you want to basically be able to reuse the hardware circuitry. You don't need to have an antenna. Great for this. Do you have a follow-up question?
Yeah, how much power does this use compared to just having a tiny antenna, even with the bad antenna?
Yes. and I'm like, dang, I should have included those figures because I had them in a prior slide. I just excluded them just for time purposes. But yeah, we have a figure here. Um, let's see if I can somehow get this here. Yeah, we have a graph. So I'm gonna stop share. I'm gonna share this. All right. So one-to-one comparisons are like hard, so we did our best to like make sure that it was as one-to-one. So we basically wanted to transmit like, per same amount of data, like how much power consumption, so then we basically looked at different tool chains, so like BOE, Zigbee, Wi-Fi, LoRa. And then on the y-axis, it's normalized with respect to the TI board. So basically, like the orange bar, basically is like our work. It's gonna be 1. You can see how like BOE is like the green bar is like
Yeah, more questions.
Yeah.
What was the range then? Is it similar range or is it shorter?
for BOE.
No, for your work.
Oh yeah, so for my work, experimentally, our range is I would say around 15 meters.
15 meters.
Yeah. So, but like BOE, like for instance, Wi-Fi can like tens, hundreds, like it can go farther. But it's at that trade-off, right? So,
Just the CPU itself, like changing power,
Mhm.
not about 15 meters.
Yeah.
Okay.
Yeah. So that's line of sight though. Yeah. So if you have a direct line of sight, you're able to measure that. Obviously, like if there's obstructions, like noises, it could change some of those. But that's kind of what we were able to measure. But yeah, this is essentially the power. You can see it's more for like Wi-Fi. But like for instance, like BOE is designed to be like a lightweight, but like we're still able to improve upon BOE as well. So now I will go back to this. All right, I guess we're doing good on time. We're ending at we'll end at 5:50, hopefully beforehand. But yes. Principle to take away is side channels can be used for many things: anomaly detection, tracing, device detection, communication, etc. Pretty neat. Did not I think when I came into at UCLA, like I think I've learned a lot like about side channels and how they can be used for useful purposes, and it kind of opened my thinking towards this, where I think there's a lot of takeaways that we can get from this, and that side channels are always there, like they're never going to go away. Like the devices we use are going to change, and the systems, the SoCs that we use are going to have new attack surfaces to look at. As I said before, attacker capabilities are rising. Thinking of like all that compute power they have, the large language models, it's a lot. So there is a need for continued research. I guess from a research perspective, it's funny, like an attack is like, you're helping the community because if you find the attack, then they can defend it. And lastly, side channels, traditionally a bad thing, but they can also be a good thing. So they can help us as hopefully as much as they hurt us. But yeah, maybe they help us more. But yeah, side channels can also be a good thing. And I think the key idea is that like we have these lots of compute powers, they're doing lots of cool things for us. And if they are indeed leaking information, like why can't we use that to like the betterment of the system and of itself? But yeah, that's the end of the presentation. That's it for side channels. Thanks for listening. If you guys have questions, feel free to reach out to me. Do I have my email Oh, I do. My email is on the slides. You can reach out to me or talk to Nodder. I would love to talk with you guys more. But yeah, best of luck on this course and your projects as well.